Good morning, everyone. I'm JC Vinuta, Associate Professor in Electrical and Electronics Engineering Department, Navandi Engineering College. Today, I'm going to discuss about symmetrical fault analysis in power system analysis. We all know that the fault can be classified into two types: symmetrical fault as well as unsymmetrical fault. So today, I'm going to discuss about the symmetrical fault analysis problems. These problems can be analyzed under two conditions. One is no load condition, another one is loaded condition. Now let us move on to the problem. So the first problem, two generators G1 and G2 are rated 15 MVA 11 kV and 10 MVA 11 kV respectively. The generators are connected to a transformer as shown in figure. Calculate the fault current when a three-phase fault occurs on the high voltage side of the transformer. So in this problem, two generators and one transformer which is connected, and the ratings of each and every component is specified in this problem. And here it is required to calculate the fault current when a three-phase fault occurs at high tension side of the transformer. So the transformer which is rated as 11 bar 66 kV. So here the fault has been occurred at this high tension terminal, that is at this side the fault has been occurred. Now we have to calculate the fault current at this terminal. So in order to find the fault current, first we need to calculate the value of various reactances of the components like generator G1, G2, transformer, etc. For this, the first step is nothing but um, we need to assume new MVA value as well as KV value. So let us see any value it is specified for this MVA. So in the problem, nothing is given for MVA and KV. So we have to take the highest rating of MVA in this circuit. So if you see in this 15 MVA is the highest of the all the components. For the second generated, it is 10 MVA. For transformer, it is 15 MVA. So normally we will choose the generator ratings as the base value. So this 15 MVA that will be same as the entire problem. And the second step is we need to find KV for all the sections. So wherever we have the transformer, in that case, we need to calculate new KVB. For this, we have to divide the entire problem into various sections. Wherever we have the transformer, we have to divide that into various sections. So here we have the transformer, so that we can divide this as the first section, and this will be the second section. This will be the second section. So for this first section as well as section 2, we need to calculate KVB new. So for this first, we can take generator 1. So for this, the base KV is nothing but 11 kV. Since the generator ratings are chosen as new base values, its KVB value will not change, so that its KVB new, that is equal to 11 kV. And coming to the second section, this is your second section. So if you take the second section for transformer, it is nothing but high tension side. So that we have to apply the formula KVB on HT side of transformer. So the formula is KVB on LT side of transformer into HT voltage rating divided by LT voltage rating. So what is KVB on LT side of transformer? Here you can see. So here already we have taken KVB new, that is equal to 11 kV. So that will be taken as new kV. Now here this KVB on LT side of transformer, low tension side of transformer is 11, and HT voltage rating divided by LT voltage rating of a particular transformer. It is nothing but 66 divided by 11. So here this 11 and this 11 get cancelled. So it is nothing but 66 kV. So this is the KVB new for section 2. So for the section 2 new KVB, that is equal to 66 kV. So for section 1 it is 11 kV, and for section 2 it is 66 kV. Now after calculating this KVB, we need to calculate the per unit reactance for each and every component in the system. So first one is generator 1. So for this generator 1, kVB new that is equal to 11 kV. For the section 1, here the generator 1 is connected and the new kVB that is equal to 11 kV. So what is its new MVA value? It is 15 MVA. So for entire calculation, it remains constant. So now we can apply the formula Z per unit new that is equal to Z per unit old into kVB old by kVB new the whole square into MVAB new divided to MVAB old. So this ZPU old. So this is the old value of the generator. So whatever the value specified in the problem, that value we have to choose as the old value. So this J.1 is the old base value. Then kVB old by kVB new for generator 1. Generator 1 kVB new is equal to 11 kV. So what is old value? It is nothing but given value. This is also 11 kV. So old by new that is equal to 11 divided by 11 the whole square. Similarly MVAB new. So MVAB new is equal to 15 MV and MVAB old for the generator 1 that is also 15. So MVAB new divided by old that is equal to 15 divided by 15. So this gets cancelled, this gets cancelled. So the answer is J.1 per unit. And similarly for the section 2, we have to calculate Z per unit new, that is for generator 2. So for generator 2, it is Z per unit old in the same formula and we have to apply, we have to substitute the value of Z per unit old, kVB old by new and MVAB new by old. For generator 2, MVAB new is 15, MVAB new is 15 and MVAB old is nothing but 10 MVA. This is for second generator. So we can substitute all the values and if we find the value, it is nothing but J.15 per unit. This is for generator 2. Similarly, we can calculate the value of the per unit reactance of transformer. So same formula. So Z per unit new is equal to Z per unit old into kVB old by new the whole square into MVAB new by MVAB old. So for transformer, what is Z per unit old? It is nothing but 0.06. So that J.06 we can substitute here. kVAB old is 11 and new is also 11 and then MVAB new is 15 and MVAB old for this transformer that is 15 MVA. So 15 divided by 15 is 1, 11 by 11 is 1. So the answer is J.06 per unit. This is the new per unit reactance of transformer. Now, we have calculated the per unit reactance of all the components in the system. So, we can draw the reactance diagram. So, while drawing the reactance diagram, generator will be represented by its source and its reactance. So, here two generators as per our diagram, two generators are connected in parallel that will be connected in series with the transformer. So, we can draw the reactance diagram here. First generator and its reactance, second generator and its reactance. Then after connecting these two generators, we can draw the reactance for the transformer. Now from this, we have drawn the reactance diagram. Next, here we need to calculate the fault current. So in order to calculate the fault current, we have to redraw the diagram. That is, we need to use Thevenin's theorem to calculate the fault current. So for this, we have to assume the voltage source to be 1 angle 0 degrees. So for two voltage sources, we can take the value as 1 angle 0 degrees. Then we can mark the same reactance values. And here at this point, at the terminal of the transformer only, the fault has been occurred. So at this faulted point, we can mark the voltages, open circuit voltages VTH. Now, to find out the value of Thevenin's impedance, we have to short circuit all the voltage sources. So here there are two voltage sources are there. We can short circuit these two voltage sources. If you short circuit, then we can redraw the diagram so that it will be like this. The diagram will be like this. Now we have to simplify this diagram to calculate the value of ZTH. Now these two reactances J.1, J.15, both are connected in parallel. That will be connected in series with J.06. So first for the parallel connection, here we can write. So if two resistances or two impedances are connected in parallel, then we will write R1 R2 divided by R1 plus R2. Here also J.1 into J.15 divided by J.1 plus J.15. So it is nothing but J.06. This J.06 that will be connected in series with this J.06. Now these two reactances are connected in series so that we can add these two reactances. So it is J.12. The value of ZS is nothing but series impedance is nothing but J.12. Now we can draw the final equivalent circuit. Here we have ZTH. This is the value of ZTH. From this value of ZTH, we can draw the Thevenin's equivalent circuit. So the Thevenin's equivalent circuit, which consists of the Thevenin's voltage as well as ZTH. Its voltage is 1 angle 0 degrees and its, the impedance is J.12. And here, this is the fault point F. Now we can calculate the fault current. So in order to find the faulty current, we can short circuit the terminals of the transformer. So here at the terminals, that is at the end of the circuit, the fault has been occurred. So these two terminals are short circuited. So if the path is short circuited, the fault current that will be flows through the faulty terminal. And we know the formula IF is equal to VTH divided by ZTH. So what is VTH? It is 1 angle 0 degrees. And ZTH, just now we have calculated its value is nothing but J.12. So 1 divided by 0.12 is nothing but 8.33. If you take this J from the denominator to the numerator, it becomes minus J. So the answer is minus J 8.33 per unit. Now, I require the answer in terms of actual unit. So, in order to find the current, the fault current in amperes, we can rewrite the expression. So, we know that per unit value is equal to actual value divided by base value. So, I per unit that is equal to actual value divided by base value. So, I actual divided by I base. I actual divided by I base. Okay, so from this expression, I need this actual value. I actual. We need to calculate this I actual. So in order to find this I actual, we can multiply the per unit value with the base value so that we can calculate the value of actual value of the fault current. So to find the value of I actual, we require this I per unit and I base. This I per unit we have calculated just now, and we have to calculate the value of I base. So what is the formula to calculate base current? It is nothing but MVAB divided by root 3 into KVB. Since both the thing, that is both MVAB and KV in the same unit, then only we can get the answer in terms of amperes. So that this MVA it will be converted into VA, and this kilovolt that will be, that is we can convert we can convert this MVA into kV. Okay, and already here it is in kV. So KK get cancelled. So 15 into 10 power 3 divided by root 3 into 11. So the answer is 783.3 amperes. Now, if you multiply this per unit value with the base value, we can calculate the value of the faulty current in terms of kiloamps. So here the per unit value is J 8.33 into the base current is 787.3. So that if you multiply these two values, that product, that is nothing but the value of current in terms of kiloamps. So this is the value of the faulty current in terms of kiloamps. Now here we need to calculate the value of the subtransient fault current. So in order to find the subtransient current in the generator, we have to redraw the circuit diagram. So how to draw the circuit diagram? Here we have two generators. That is, we need to calculate the subtransient current through generator G1 and generator G2. So for this, we can redraw the equivalent circuit with two generators G1 and G2. So first generator and its corresponding reactance, second generator and its corresponding reactance. Okay, and its voltage is 1 angle 0 degrees. Now here, this F point that represents the faulty point. Okay, so the fault current IF that will be flowing through the circuit from this faulty point towards generator 1 and towards generator 2. So if you want to calculate IG1 double dash, we need to apply current division technique. So what is current division technique? The total current into its opposite resistance divided by total resistances. So what is the total current in the circuit? It is nothing but IF. So IF into what is the opposite resistance? Since we are calculating IG1, its opposite resistance is J.15 divided by total resistance J.1 plus J.15. So if you substitute the value for IF and if you calculate the answer, the value of IG1 double dash is equal to J5 per unit. Similarly, we have to calculate the current through the second generator IG double dash. So double dash, it represents subtransient current. Um, Here, the formula current division technique is the total current into its opposite resistance. Since we are calculating the current through second generator, the opposite resistance is J.1 divided by total resistances or J.1, J.15. And so, this is the value of IG2 double dash and this is the value of IG1 double dash. So, in this problem, to find the fault current, we have to use Thevenin's theorem as well as in order to find the current through, that is substantial current through reactances, we have to use current division technique. Thank you.